A little review from the previous session. We talked about phase diagram, and this is a sugar water or syrup phase diagram. The water sugar has a solubility limit at room temperature up to here 65% of sugar can be added to the water, um, but if you raise the temperature, the equilibrium system uh, is upset temporarily. Then after some time, um, the system gets in equilibrium state, and you see for example, the increasing the temperature will be able to add more sugar into the water. Beyond this solubility limit, whatever sugar you add, so it's gonna settle um, to the bottom of the beaker. We can have the same equilibrium state in solid elements. For example, here we talked that if we mix copper atom and nickel atom, we can have different phases. As you see, this phase we have unique pattern which is completely different from this pattern. So this is again copper and nickel, but the way they are arranged is different from this one. So this is called phase B, and this is called phase A, and this is solid solution of these two atoms. And we also discussed some of the terms that we use in solid solution. For example, solute. What is the solute? Solute is a minor element that is going to be added to the solvent. So solute, for example, in the sugar and water, the solute is sugar, and solvent is going to be the major element, such as water in the syrup example. When we are talking about crystal structure, the solvent is going to be maintained during alloying process, and alloy is called solid solution. We discussed that we have two types of solid solutions. One is substitutional solid solution. If the size of solute atom is similar to the solvent atom, this one is solute and this is solvent. Major element in the solution is is called solvent, and this is a minor element. So you see both atoms are the same size. We said that brass is one example, the zinc and copper. And here we have interstitial solid solution where we have a smaller atom as a solute atom, which is much smaller than the major element or the solvent. A good example is steel, where we have carbon atom as a solute, and the major element is going to be Fe. Also, we discussed the phase diagram of two components, for example, copper and nickel. We mentioned that copper and nickel has three area. One area which is solid. If we change the composition from, for example, this is copper. Pure copper. If we increase the nickel composition into the copper, then the alloy will have a higher melting temperature, because if you go more toward nickel, because nickel has higher temperature, so the melting temperature increases. And if you go toward the copper, then the melting temperature is going to be lowered. And then we have a liquid region, and there is an area, there is a certain composition and temperature that we have both liquid and solid alloy together coexist in that system. And we also discussed how we can calculate the amount of these phases, for example liquid, and how much solid we have in that system. In the phase diagram, we sometimes we need to determine the amount of phases. In here we have copper nickel, right? If we have one phase, for example here this region we have liquid, right? This is one phase, and also here we have one solid phase. So if you want to find out the composition for any point, for example point A, if you want to find out the composition of point A, it's going to be trivial, it's easy. You just need to locate the temperature. First of all, they say for example the temperature is given and composition is given, then you can say this is a phase. You construct these two lines and they cross each other at this point, you say we have one phase. But if you are in this point, you have 1400 degrees Celsius, and then you have the composition is given 40, then you reach at this point, so again the phase is going to be liquid. You have only one phase. But the tricky point is when you are in this between these two lines, the liquidest line and solidest line. So there is an equation that you can use to determine the amount of phase in this region. Okay, here the instruction is written for you later. You can download the PDF file of this presentation in the Blackboard and follow this instruction to determine the amount of phase when you are dealing with two phases. For example, in this case we have alpha. Alpha is a solid solution. Of copper and nickel, right? And then we have liquid and alpha. So the first way is to construct a tie line. For example, in the problem or in the question, the amount of composition is given, Z is C0, right? And then the temperature also is given, to 1250, and then you cross these two lines and construct them, and then they cross each other at this point B. So we are in this two phases. Now we want to find out if we have to draw a horizontal line, they call it the tie line, until they cross this solidest and liquidest line. Remember, this is going to be horizontal line, not vertical line. And then the overall alloy composition is going to be located on the tie line. The fraction of one phase is computed by taking the length of the tie line from the overall alloy composition to the phase boundary for the other phase and dividing by the total tie length. Here is the equation. So you have, for example, if you want to calculate the amount of liquid phase, remember this is going to be a liquid, You need to calculate this area. You have to subtract this amount, the alloy composition, from this point. So it's called S. And then divide this S by R and S. R is going to be C0 minus CL, right? And then that gives you a composition of liquid. If you want to do for the alpha, equation is the same almost. You just need to change this equation is similar, but we just replace SR with this composition symbol. So let's look at one example for calculating liquid phase and alpha phase. If you are given the temperature and composition, right? Here we have B. Based on these 2 points, we can construct 2 lines and then find out where the B, or the point of interest, is located. We see that it's between this solidus and liquidus line, and we have 2 phases, alpha and liquid. So we need to construct this tie line, okay, and then we can determine the amount of liquid phase. Liquid phase is this length. You have to determine first S phase divided by the total length. Then if you do that, you can calculate the portion of liquid phase. And similarly, we can do for the other phase, which is alpha. We have to calculate this portion and divide it by this portion, which is this equation. So you can subtract this part from from 1, then you can get alpha phase. This is another way to calculate the amount of alpha phase. Here we want to look at the microstructure of copper nickel system, and this alloy is called isomorphous alloy because in liquid state and solid state both elements are dissolved into each other completely. So we have a solid solubility. We have a complete solid solubility. And if we consider point A and then we drop the temperature until it reaches this point, we start having forming solid material, and that solid material, as you see, is a red region, is small circles here inside the orange or yellow circle. So the yellow is liquid, because at that point we have all liquid, and then when we drop the temperature, it reaches the liquidus point, liquidus line, and then at that point we will have alpha, and alpha will have 49% nickel. So if you want to find out how what is the composition of those little spots, so you have to construct a line, horizontal line. Again, horizontal line is important. you have to construct a line until it reaches the solidus point, solidus line, and then you can determine the amount of nickel. How? Just in here you point across a vertical line, construct a vertical line, then you see this point is going to be 46%, and then the composition of those little circles is going to be 46. As you go down, you need to follow this solidus line, and here this is an microstructure of that point, and that point we have a solid material will follow the composition of these points. At this point the composition is although the area, the part, or this component are getting larger, but their composition is decreasing. Initially it was 46, now it's 43. And then we have a liquid area, liquid phase here, and that follows this liquidus point, the liquidus line. So the liquidus line has 32% nickel. When we say 32% nickel, how about copper? If you want to find out how much copper you have in that nickel, you just need to subtract this amount from 100. Then you can find out how much copper you have in there. So if you subtract this amount, it gives you, let me erase this. You can find this is 68% copper, right? The same thing for this region. So if you have 43% nickel, how much copper I have there? You just again subtract this amount from 100, then you find 57% copper. Simple. Again, we need to come down. When we reach point D, we reach the solidus point, solidus line. We have A, which has 35% nickel, and liquid. The liquid is going to be 24% nickel. If you go a little down, then you have one phase, and the phase is going to contain 35% nickel, follows this point, and then 65% copper. So this is the way we can find the microstructure of the alloy in different temperatures, starting from liquid, ending in the solid state. So far we discussed the phase diagram of the simple alloy copper nickel alloy. Here we are gonna discuss this copper iron carbon system, very well known system, phase diagram, and this is important for iron and carbon. And if you want to understand the phase diagram of iron carbon, there are some terms that you should know. First, pure iron is a polymorphism, so it means when you heat it, it will have a different type of crystal structure. Here you see the temperature and the property of the pure iron. From the room temperature up to 700, we have BCC structure. It's a magnetic iron, but when it goes above that temperature, it loses the magnetic property, but still it has a BCC structure. This one, after 912, it transformed to gamma. Remember, this is a gamma or FCC. We call alpha iron or ferrite. Ferrite. I explain their property in this slide one by one. These structure has unique mechanical properties. Some of them are hard, some of them are tough, some of them are soft. At room temperature, we have a BCC crystal structure, and it's called ferrite. And then we have austenite. Gamma iron is also called austenite, FCC. All of them, they refer this iron. Gamma, austenite, FCC, iron. Above that temperature, above this point, it reverts back to BCC, but that type of iron is not called ferrite, alpha ferrite. It's called delta ferrite. Delta ferrite is different from alpha ferrite, and this is not very important. The most important are FCC and I mean the gamma iron and alpha iron, alpha ferrite. This one important, and this is the second one. We have a term called iron carbide or cementite or Fe3C. It's an intermediate compound formed at 66.7 weight% of carbon. So if you have this much carbon and the remaining is going to be for example 93% Fe, you will form cementite. Cementite is very hard material. So typically all the steel we focus in industry, and cast irons, they have carbon content less than this amount. If you have a carbon content more than this, it's not useful in industry, in engineering application. And we mentioned that the carbon is an interstitial impurity. So we have a solid solution which is in a type of interstitial because it sits between iron atoms because it's so small. And carbon can dissolve in all of these phases. But it's important that the solubility of carbon in these phases are different. In gamma, the solubility limit of carbon in gamma is high. In alpha ferrite is low. This is a phase diagram for iron carbon, and as you see we have here the composition, and this axis is temperature, right? And one thing that you can notice, this is much more complicated comparing with the binary system of copper and nickel. In copper and nickel, we had only 3 regions, but here we have many more. As I mentioned before, we are interested up to 6.7% of carbon, and in that amount of carbon gives you cementite 100%, and we call that solution cementite, Fe3C. Okay, and the cementite is brittle material, hard material. We discussed the phases. As you see here, we have various phases. Discuss them later in the next slides, but keep that in mind. From zero, actually from this point up to this composition, we call this alloy steel. Or carbon steel. And from here, in this region, above 2.4 up to 6.7% carbon, we call it cast iron. Okay. As I mentioned before, we have three phases, phases for iron, ferrite, austenite, and delta ferrite. But we are interested mostly in alpha and gamma. This is gamma, right? And ferrite, iron, or austenite iron, they both have some solubility, carbon solubility in them. The maximum solubility of carbon in austenite is 2.14 weight%, and that occurs at this temperature. But the solubility of carbon in ferrite is way lower. So it says solubility of carbon in austenite is 100 times greater than the maximum of ferrite, BCC ferrite, or alpha. Ferrite is a relatively soft material, and it is magnetic. I show this phases in the carbon steel iron carbon phase diagram. The next slide. Here is the microstructure of ferrite and austenite under microscope. You see these black lines? These are grain and boundary. This is grain. As we mentioned before, grain, all the unit cells within the grain have the same direction, the same arrangement, but this one may have a different arrangement. But again, all of the unit cell in that within that grain will have same arrangement. This is a phase. This is a grain for austenite. Okay, here this is the phase diagram of FEC, or iron carbon. We have several reactions in this phase diagram that I'm going to describe. The first reaction is that at point A, you see we have at this area we have liquid, and then below that point we have gamma plus cementite, right? This is cementite, we mentioned it. So this reaction can be written like this way. liquid transformed to gamma plus Fe3C. Both components are solid material. So one liquid transforms into two solid material, and this reaction is called eutectic reaction. This is not very point of interest in the carb FEC phase diagram. The next one is very important. Here we have eutectoid point, which happens at this point. It's called point a eutectoid. In the eutectoid, we have one solid material. Look, this area we don't have any liquid. We have solid material, austenite or gamma, and it transforms to two solid material, alpha and Fe3C. And the composition of that reaction is 0.76. And the composition of this reaction, eutectic reaction, is 4.3. When we are in the austenite region, we have grain, and grain will look like this, just a schematic. Then when it transforms, it's all of them one phase, right? But we have multiple grain in it. But when we have a reaction like this, we have alternating layers of Fe3C and alpha. So they are separate. And we have two phases. Blue is alpha, ferrite, soft, and this is cementite and hard, these red regions. If you look at this microstructure under microscope, we see the similar this type of picture. It's very small, 120 micrometer. And the combinations, sometimes they call this combination perlite, alternating layer of alpha and cementite phase. They are not one phase, they are separate. I mentioned that we are interested in this area where we have gamma or austenite that is transformed to alpha ferrite and cementite, and this gives you a unique arrangement, and that arrangement is called perlite. The reason we call perlite because it is similar to pearl. If we are looking at the steel with this composition 0.76% carbon, it's called eutectoid steel. But if we are looking at steel, as I said before, from here to here, this area is we call this composition a steel. If we look at the steel or that has composition less than 0.76, we call that type of steel hypoeutectoid steel. When gamma again transforms to alpha and cementite, we have a different arrangement. We start getting some of this alpha starts forming at this point. In this region we have alpha plus gamma. So you have this alpha, and when you reach this point, we have all alpha plus Fe3C. The remaining gamma, you see, we have some of the gamma converted, transformed to alpha, but we still have some of gamma left. That the remaining gamma transformed to pearlite or this combination. The next steel is called hyper-eutectoid steel, where we have carbon in the steel more than 0.76%, and similar to previous slide, we have gamma that is going to be transformed. So this is eutectoid line, right? This is austenite transformation line. Here at this point, some portion of gamma transformed to Fe3C. But here, on the previous slide, we mentioned that some portion of gamma was transformed to alpha. Here, because we have more, cementite or Fe3C, portions of gamma is going to be transformed to this phase. Red region is cementite. Then, as the cooling progresses, then the remaining gamma transformed to pearlite with this pearlite arrangement. This is the actual FEC or iron carbon phase diagram. As you see, again, this is much more complicated than the phase diagram I described. So I don't want you to memorize all these lines. For example, here between this point and this point we have a line. It's called ACM line, and then from this point to this point there is another line, so it has a name. This line, all of them, they have a name or temperature, composition. Some of the composition, some of the name, for example, what phase we have at this region, you need to memorize. For example, in this region, what we have, pearlite and ferrite, which is alpha, and cementite. I want you to memorize this name. This is delta. This one here, this composition, then here this area we have alpha. So I want you just learn this terms, and that's all I like you to know about this phase diagram. And the reaction I described, the reaction between we have eutectoid, where gamma transform to pearlite and pearlite, and eutectic transformation. This reaction you need to learn as well. I mentioned several phases in iron carbon steel phase diagram. Here are the summary of their characteristics. For example, for ferrite, we have solid solution of carbon in BCC from room temperature to 900 degrees Celsius. The maximum solubility of carbon in iron is this 0.22% at temperature of 700 degrees Celsius, and this is called alpha ferrite. And this is a soft phase in iron carbon phase diagram. The next phase is called cementite. We mentioned it's Fe3C. It's intermetallic compound. Intermetallic compound of with iron, and maximum solubility is 6.67%, and it's the hardest and most brittle phase among iron carbon phases. The next one is austenite. It's not stable at room temperature. It mostly exists between 900 degrees Celsius up to 1300 degrees Celsius. The maximum solubility of carbon in this phase is 2.11%, which happens at 1100 degrees Celsius. It's a very tough phase. Strength is high, and it has a good amount of ductility. But remember, if it is possible to have austenite at room temperature. This is a topic of for other courses called heat treatment, that we can add alloy to the steel to make austenite stable at room temperature. Those elements are called those alloying elements are called austenite stabilizer. And then we have perlite, a mixture of ferrite and cementite. They are arranged like a pearl. We can have 100% perlite at 700 degrees Celsius. This is the Uteck tweed point. A soft phase compared to austenite, but it's a little harder than ferrite, because it contains cementite in that mixture. The next phase is that we didn't mention before is called martensite, and it exists in steel. That is the main reason we have hard steel, because we have martensite. There, it's a very hard material, hard phase. But how can we get martensite? Martensite, the main reason is that the carbon solubility of gamma or austenite is more than alpha, right? So this is a structure of gamma. This is a structure of BCC or ferrite. As you see here, we have carbon that is sitting between these atoms, because we have a larger space between these two atoms, but it doesn't have that space in this structure, this unit cell. When we cool the steel, the carbon is gonna diffuse out. It doesn't want to stay there, because it is the BCC, the FCC is transforming. So if we don't have FCC anymore, right? But what happens, it requires time to diffuse out. If you keep if you cool it down very rapidly, or another way to say, you quench the material, you don't provide time for carbon to diffuse out, the carbon is going to be trapped into that unit cell. When it traps, it provides a stretching to that unit cell, and that unit cell, as you see, it's not cube anymore. It's called tetragonal, BCT, body center tetragonal martensite. This is another way to show the martensite structure. And if you have this type of structure, with carbon sitting in that side, and it provides tension, so it makes it very brittle and hard material. It's not soft material similar to this phase. This micrograph shows the martensite, which are a needle shape. And these are random orientation. As you see here, they are in random direction.